let's talk about a material that's basically a modern marvel. Advanced composites are the secret sauce in some of our most incredible machines. But they also come with a hidden danger, one that's a massive challenge for engineers.
So, what makes them so special? I mean, just think about it. A material that's stronger than steel but weighs less than aluminum. It sounds like science fiction, right? But it's why they're in everything from the supercars we dream of to the jet engines that fly us around the world, and even those giant blades on wind turbines. They are at the very heart of next gen manufacturing.
Okay, but here's the catch. With all that amazing strength comes a really tricky vulnerability. See, when metal breaks, it bends, it cracks, you can see it. But when a composite gets damaged, the real problem might be totally invisible. And that brings up two huge questions. What happens when they do break? And how on earth do you fix a problem you can't even see? And this right here, this shows you exactly what I'm talking about. The real danger isn't some crack on the surface. Nope. It's a failure inside the material, the layers separating, or a defect very deep where no one can see it. This isn't just a simple scratch. It's a super high-stakes puzzle, especially when the safety of something like a jet wing is on the line.
So in this explainer, we're going to break down the entire story. We'll start with this composite conundrum, then look at how these materials get certified, dive into how you repair them, check out how engineers literally see the unseen, and finally, look at what's next, a circular future for composites. All right, let's start at the very beginning. Before one of these composite parts can ever be used, it has to be proven to be absolutely 100% safe. And this isn't just a quick quality check, it's an incredibly intense process. You know, for something like an airplane part, every single component has to go through this insane gauntlet of tests. The rulebook for this is a massive, super detailed handbook called CMH17. It's basically the Bible for proving these materials can handle the incredible stresses of flight, not just once, but safely for years and years. And what's wild is that these rules are always changing. This table shows it perfectly. A standard like CMH17 isn't set in stone. It's constantly being updated. You can see right here how the latest version is tackling totally new challenges. The old one barely talked about parts that mix metal and composites, but the new one, it's adding whole new sections on it. It's also pushing for way more guidance on long-term aging, making sure these things are safe for decades out. So, okay, the part is certified, it's out in the world, but then life happens, right? A bird strike, a maintenance crew drops a tool, something goes wrong. Do you just throw out a multi-million-dollar part? Well, not if you can avoid it. Replacing these things is ridiculously expensive, takes forever to get a new one, and is a nightmare to install. That's why, for these super valuable parts, repair isn't just a nice-to-have, it's an absolute necessity. It's what makes using these amazing materials even possible in the real world. And a real structural repair is this super precise 4-step dance. First up is assessment, finding all the damage, especially the invisible stuff. Then you prep the surface, carefully grinding away the bad material to get a perfect bond. Third, you apply new layers of composite, making sure the fibers are oriented just right to restore strength. And finally, you cure it, using vacuum and heat to create this incredibly strong, permanent bond. It's really more like surgery than a simple patch job. Okay, so the repair is done. On the outside, it looks perfect. But remember our big problem? The damage was hidden. So how can you be absolutely sure the fix worked deep down inside the part? Well, the answer is something called non-destructive testing, or NDT. And you should think of it like giving engineers a set of superpowers. These are incredible techniques that let them literally see inside a part to check its health, all without ever damaging it. And the NDT toolbox is just wow. It's incredibly high-tech. You've got things like laser shearography that can spot tiny surface changes that mean there's a problem deep inside. Then you have advanced X-ray and microwave methods that can see right through the material. Each tool is like a different set of high-tech senses, finding flaws the human eye would never, ever catch. So the whole point here is total, complete verification. Engineers use these tools to inspect every single piece of that repair, the new patch itself, that all-important bond where it meets the original parts, and even the material underneath it all. It's the only way to be sure that the fix is safe, strong, and gonna last. So far, we've been really focused on certifying and fixing a single part. But let's zoom out now and look at the really big picture, because the conversation around these next-gen materials isn't just about performance anymore. It's about sustainability and the entire life cycle. And this chart, this says it all. Just look at the numbers for a simple car fender. Repairing it creates about 5.7 kilograms of CO2, but replacing it, over 26 kilograms. That's a huge difference. Repair isn't just cheaper, it is a massive win for sustainability. But that brings us to the final and maybe the biggest challenge of all. What happens when these giant composite structures, like an entire airplane wing or a massive wind turbine blade, get to the end of their life? What do we do then? The scale of this problem is, well, it's staggering. Just from wind turbines alone, we could be looking at over 1 million tons of blade material waste heading to landfills every single year. We just can't keep throwing this incredible material away. We have to find a circular solution. And this is where it gets really cool. People are coming up with brilliant solutions. Take this idea, the blade pole. You take old retired wind turbine blades, cut them up into big, strong sections, and then you repurpose them as utility poles for high voltage power lines. You're literally turning waste into essential infrastructure that can last for decades. How smart is that? So, it's pretty clear that the whole mindset around advanced manufacturing is shifting. It's not enough anymore to just invent a material that's stronger or lighter. We've got to think bigger. The real goal now is to build a complete life cycle that never really ends. One where these materials are certified, used, repaired, and then at the very end, repurposed into something new. That's the true challenge, and it's the biggest opportunity. The only question left is, are we ready for it?